Hey guys, so this is pretty much the closing in on like the end of momentum and really the end of mechanics for this entire class, and I'll explain why in a second. But the first thing we need to go over is this last term, impulse. So what does impulse mean? So impulse, let me type it out here. Impulse is equal to change in momentum. If you have a friend in life who's impulsive, I think you know those kind of people. What does an impulsive person do? They change their minds a lot. They change direction. Well, impulse is kind of like that. You change your momentum a lot if you have a high impulse. So literally by definition, delta P would be what impulse is, which is the final momentum of an object in the initial momentum. And so I can write that out as mv final minus mv initial. So this is just how you get impulse. Impulse is for one object only. It's not about both objects, only about one object. We can also relate it to F net times T. And I'm not going to break down how you get this, but it's basically reusing Newton's laws, and we're going to see all three of Newton's laws involved in these problems again. Now, if you want to cut the middleman out, you can say, oh, these delta P's are equal, so F net times T is equal to mv final minus mv initial. Now, just to be clear, all these equations can be used. If they're asking for impulse, you could use this one, you could use this one. It kind of depends on what information they're giving you. Let's start answering some of these problems, see where you get. And my suggestion is try to solve all these problems and then come back and see what I'm discussing. Let's start with this first one. You're on roller skates, you throw a ball forwards, you go backwards. But what if you fake throw it? Don't you think about it? You can imagine in space, you can probably flip your body around, like you can spin in circles by rotating your body, but you can't move your body unless you release something. So the idea of this problem is that if you pretend to throw the ball, you just hold on to it, said you will not move backwards because you never sent out a positive momentum to create a negative and equal and opposite momentum. So that's what I would say there. All right. Hopefully that's not too difficult to imagine there. Well, let's actually put some numbers on here, and I want you to ask yourself, all right, we have a clay ball. It's going to strike a wall. So we have a wall, and we have one scenario where, you've got a clay ball that's heading to the wall and it just sticks there, versus a super ball. Think of like a kickball. It goes into the wall and then it leaves the wall a little slower than it was before, 0.8 meters per second. Which one has the greater impulse? What do you think? Pause the video, think about it, stick aside. Let's see what you get. All right, most people that when I ask this question, they'll say the clay ball, and they'll say the clay ball is moving towards the wall. It hits the wall, it stops moving. So that has that much impulse done to it, enough to stop it, while the other object hits the wall and bounces back, so it still has some velocity. So shouldn't that be, it shouldn't be as much as something that completely stopped. Well, let's try to work it out. So we have clay versus super ball. So let's see, delta P is equal to mv final minus mv initial. I'm going to keep the masses as 50 grams. I'm not going to convert it. As long as everything's the same, it's fine. So 50 times my final velocity for the clay is 0 because it gets stuck on the wall. My initial is 1. So I end with negative 50 grams meters per second. You might ask yourself, wait a minute, Mr. Erickson, why is it negative? Well, if we're assuming towards the wall is positive, then you need this negative momentum to stop the object. So that's what's happening there. That is enough momentum to stop this object's initial momentum. All right, let's do it for the super ball. So the super ball, it ends going negative 0.8 because it's going away from the wall, and it has the same initial. When you plug this all in, you'll get negative 90 grams meters per second. So if we're looking at magnitudes, the Super Ball has a lot more change in its momentum. And I think it makes sense if you think about you need so much energy to stop an object. In the second scenario, we had the Super Ball had to be reverse direction as well. So not only did it stop it, it also had to push it the other way. So that's why this has ended up in this situation. And I had to switch rooms, so sorry if my audio has changed a lot. So let's go to problem 3 here. So Hummer versus the Volkswagen Beetle. Some context. If you don't know what a Hummer is, it's a very big car, very massive car. A Volkswagen Beetle, the opposite, very small. Maybe not like a smart car, but definitely very small. Which vehicle will experience the greatest force of impact? Let you guys answer this, but I'm going to go right in and explain this. If you remember from previous units, Newton's third law, equal and opposite. And I'm not going to explain too much, but is always present. Even though the beetle gets more beat up, that's more of an answer for like the material of the beetle. It's smaller, it's more fragile, the way it's set up. That's a different question for why it gets beat up, but they still experience the same forces in between them, equal and opposite. And greatest change in momentum, well, if Newton's third law is active, and also what we know about Newton's second law, then this should also be equal and opposite. So delta P of the Hummer should equal delta P of the Beetle. So the question is now, what will experience the greatest acceleration? If this is true, if part B is true, then let's do some momentum situations. Let's say the momentum should be the same. Delta P is that. So if you have a change in momentum of 100 and your mass is 100, then your velocity is going to equal 1. But if you have a change in momentum of 100 again and your mass is 1, then your velocity is going to be 100. Your V will be 100. Let me draw this so that's accurate. So your V will be equal to 100. So the top I have is similar to what the Hummer would be versus the Beetle. Now, they're not 100 times difference in mass. I don't think so, at least. But, yeah, that's what would happen there. Similar situation. The smaller object has to go faster to match the momentum change. All right, here's the last problem we have of this worksheet. And this is probably the most important concept in momentum. Why momentum is taught so much in these classes is actually kind of our idea of why automobiles or why like airbags actually work. That's pretty much all of our mechanics have been getting to this point. So why do we want airbags in a car versus no airbags? They call it padded dashboards versus hard dashboards. Think of just an airbag. Why do we like an airbag? And I'll give you a hint. There's a couple ways to think about it. I like to think of it of a delta P equals to F net times T kind of equation. So I'll let you guys think about it, and then we'll talk about it. All right, so imagine you're in a car, and you're driving into a brick wall, and your car, no matter how fast you go, even if you're going 60 miles per hour to start, you always end at 0 miles per hour when you crash into this wall. So you always have this change of momentum. It's always the same. It's always you're losing all of your velocity. And so you're losing all your momentum. So your change is, let's just say it's 100 again. Now, if you want to make this net force smaller on you, what do you have to do? Well, you need to either increase or decrease this time. Let's say we have a time of 10 seconds. Well, then your F net you're experiencing is 10 newtons over that time period. We do the same thing, but it's 100. Your F net, or sorry, not 100 seconds, 1 second, then your F net will be 100 newtons. Now, I just chose some random numbers here, but what's happened is when you have 10 times as long as the collision, you actually experience 10 times less force within that time frame. The longer a collision takes to occur, the less forces can hit you in that moment. So you can spread out the force over time. So if you think about an airbag, the moment the airbag comes out, it meets you as you get into a crash. It hits your face as your face starts moving forward. And if you watch those videos of people with the airbags, their face is still moving towards the dashboard. And so eventually you reach that dashboard, but the pillows increase that time so much in that collision, it slowed you down. So anything padded, anything like grass versus concrete, all of these are increasing the collision time and decreasing the amount of force you take. You can also think of it from an energy argument. The things that are more inelastic, the things that take longer for the collision to occur, those are objects that have that are dissipating the most amount of energy that's possible in that collision. And so you'll think of cars back in the 50s, think of them like Cybertrucks, like made of sheet metal. You'll see they have barely any dents in them, but people are horribly more injured back then than nowadays. Nowadays you have, think of like a Camry or something, made with plastic, made with a lot of polymers that just break as soon as a crash happens. Those are dissipating energy and they are protecting the driver. So that's kind of what this whole unit's about. I'll let you think about nylon ropes and why they're better for mountain climbers versus think of like a canvas rope. So you're climbing, you fall. Do you want to hit a nylon rope or even maybe like some stiff chains or something? No, you want nylon ropes because nylon stretches as you go down. So instead of hitting the rope with all your force, you can spread that force out over a period of time. And that's basically all I've got for y'all, and I'll see you guys. I might do one more video for Worksheet 4, but really this is all you kind of need for momentum. So we'll see if I'll do Worksheet 4.